Have you ever paused in the quiet of the night, tilted your head back, and gazed up at the vast, inky black sky shimmering with billions upon billions of stars, feeling a profound sense of awe that leaves you utterly speechless? This sensation goes far beyond simply admiring something beautiful. It is a deep, soul-stirring emotion, an overwhelming immersion in the infinite vastness and unfathomable mystery of the universe that reaches right into the core of your being. We human beings, tiny creatures living on a small blue planet floating in the immense cosmos, have carried within us an innate desire to seek answers ever since the dawn of our existence. Long ago, our ancient ancestors first looked up at those silvery points of light and realized there was something immensely greater than the limited world beneath their feet. From that moment, we have been destined to pursue solutions to the most profound questions. Where do we come from? Why do we exist in this space that is both endlessly empty and yet incredibly wondrous in ways that defy belief? You might think these are purely philosophical puzzles, filled only with speculation and no concrete answers. But that is not the case at all. Modern science, particularly the fields of astrophysics and cosmology, combined with extraordinary advancements in observational technology, from enormous ground-based radio telescopes to sophisticated satellites orbiting high above Earth, has enabled us to embark on an incredible journey through space and time. This journey allows us to touch the very physical essence of the universe itself. In the most precise terms used in physics, the universe, often referred to as the observable universe, encompasses the complete totality of everything we can interact with or influence. It includes all of space, all of time, what physicists call spacetime, and every single thing that arises from them, meaning all forms of matter and energy. Every piece of matter, from the tiniest pebble on a beach to the most massive stars burning brightly in distant galaxies, is built from fundamental particles such as electrons, photons, and quarks. These particles come together to form a vibrant, ever-moving material world that is constantly evolving and changing over immense timescales. Our story truly begins with the Big Bang, which stands as the most robust and widely accepted theory in modern cosmology. It describes the origin of everything that exists, happening approximately 13,799,000,000 years ago, that is, 13.799 billion years in the past. Before this monumental event, according to the descriptions provided by physics, all matter, time, and space were compressed into an extraordinarily dense and incredibly hot state, squeezed into a point that was almost dimensionless, known as the initial singularity or simply the singularity. This point did not exist within space or time because it was the very origin of both. It represented an extreme physical condition with infinite energy density, temperatures that could reach as high as 10 to the power of 32 degrees Kelvin, and spacetime curvature of enormous magnitude. Yet, astonishingly, this infinitesimally small point held within it the entire potential to give rise to all the matter we see in the universe today. This is the ultimate source of our existence, a beginning that emerged from absolute nothingness. When the delicate balance of potential energy inside this singularity was suddenly disrupted in a random event, a mechanism that scientists are still working hard to fully understand, the energy began transforming into matter according to the famous equation E equals mc squared, where E stands for energy, m for mass, and c for the speed of light squared. In that explosive instant, our universe was born from nothing, expanding outward in a tremendous burst. Right at that very moment, the singularity gave birth to three-dimensional space and one-dimensional time, creating the fabric of spacetime, and it even established gravity along with all the fundamental laws of physics that govern every object and interaction in existence. In the earliest phase of the universe, temperatures exceeded 100 billion degrees, and matter existed as a superhot, densely packed soup of plasma made up of basic particles like quarks, electrons, and neutrinos. As the universe expanded at a breathtaking rate and began to cool down, just 1/1,000,000th of a second after the Big Bang, quarks started combining to form heavier particles such as protons and neutrons. The most remarkable event occurred within the first 3 minutes. As temperature and density gradually decreased, a process called nucleosynthesis kicked off. Neutrons fused with protons to create the nuclei of light elements, primarily hydrogen, which makes up about 75% of the total, helium accounting for around 24%, and a tiny trace of lithium. What is truly mind-blowing is that in those brief initial 3 minutes, a staggering 98% of all ordinary matter in the form of atomic nuclei throughout the entire universe was formed. By around 300,000 years after the Big Bang, the temperature had finally dropped below a few thousand degrees Kelvin. At this critical threshold, atomic nuclei began capturing free electrons to form electrically neutral atoms, in a process known as recombination. This moment was pivotal because it suddenly made the universe transparent to light, allowing photons to travel freely through space without constant scattering. The light emitted at that exact time, after traveling for billions of years and being stretched by the ongoing expansion of the universe, had its wavelengths elongated to the extreme, shifting into the microwave range. This is the cosmic microwave background radiation, or CMB for short, that we can still detect today, with a precisely measured temperature of 2.7 degrees Kelvin. Under the relentless pull of gravity, enormous clouds of gas started clustering together, collapsing into regions of higher density. This built up enough pressure and heat to ignite nuclear fusion reactions, giving birth to the first stars, primitive galaxies, and eventually the grand, large-scale structure of the universe we observe now, including vast filaments, walls, and voids that span hundreds of millions of light-years. The validity of the Big Bang theory was powerfully reinforced by Edwin Hubble's discovery in the year 1929 of the universe's expansion, captured in what is now called Hubble's law. He observed that distant galaxies all show a red shift, their light is stretched toward the red end of the spectrum, indicating they are moving away from us, and the speed of this recession is directly proportional to their distance. A second key piece of evidence came from the accidental discovery in 1964 by Arno Penzias and Robert Wilson of the CMB, a uniform radio noise emanating equally from every direction in the sky. This provided the most direct and compelling proof imaginable. More recent data from the Planck space probe, released in the year 2013, has confirmed the standard model of cosmology and refined the universe's age to 13,799,000,000 years with an incredibly small margin of error, allowing scientists to map tiny temperature fluctuations in the CMB that seeded the formation of galaxies. Despite these triumphs, the Big Bang model still faces challenging puzzles, such as the issues of homogeneity, why the universe looks so uniform on large scales, and flatness, why its geometry is so precisely balanced. These led to the development of the inflationary theory, proposed by Alan Guth in the year 1980. This theory posits that immediately after the Big Bang, the universe underwent a sudden, exponential expansion phase lasting from about 10 to the power of -35 seconds to 10 to the power of -33 seconds. In that fleeting interval, the size of the universe ballooned by an astounding factor, possibly as much as 10 to the power of 50 times its original scale. This rapid inflation smoothed out the universe to make it perfectly flat and allowed distant regions to reach thermal equilibrium efficiently, explaining the observed uniformity. The narrative seems almost complete at this point, yet the universe harbors its greatest enigmas in plain sight, or rather, in complete invisibility: dark matter and dark energy. The full composition of the cosmos we inhabit is divided in a way that defies intuition. Only 5% consists of ordinary matter, atoms that make up stars, planets, and even our own bodies. 27% is invisible dark matter, and a whopping 68% is the mysterious dark energy. Dark matter, which accounts for 27% of the universe, is a form of matter we cannot see or detect directly with our senses or most instruments. Its presence is inferred only through the gravitational effects it exerts on the rotation speeds of galaxies and the motions of galaxy clusters. Without it, the visible stars and gas in galaxies would fly apart due to centrifugal forces, as the ordinary matter alone cannot provide enough gravity to hold them together. Dark matter acts like an invisible scaffold, structuring the cosmic web on which galaxies form and cluster. Scientists are primarily pursuing two main categories of candidates. The leading suspects are weakly interacting massive particles, often abbreviated as WIMPs, which are hypothesized to be entirely new fundamental particles that are super heavy and move relatively slowly, classifying them as cold dark matter. These particles interact with ordinary matter almost exclusively through gravity and the weak nuclear force. To hunt for them, researchers construct ultrasensitive detectors in deep underground laboratories, shielded from cosmic rays, such as the XENONNT experiment that uses tons of liquid xenon to catch the rare event of a WIMP colliding with an atomic nucleus and producing a detectable signal. Alternative ideas, like massive compact halo objects or machos, things like small black holes or brown dwarf stars made of ordinary matter but too dim to see, have been largely ruled out by observations using gravitational microlensing, where the bending of light from background stars reveals foreground masses, showing insufficient contributions from such objects. Dark energy, comprising 68% of the universe, presents an even greater puzzle. It is the force responsible for the surprising acceleration of the universe's expansion, first detected in the late 1990s through observations of Type Ia supernovae, which serve as standard candles for measuring cosmic distances. Dark energy behaves like a negative pressure or an antigravitational force inherent to spacetime itself. There are two primary models to explain it. The most widely accepted is the cosmological constant, denoted by the Greek letter lambda, suggesting that dark energy is a fixed property of empty space, quantum vacuum energy that persists even in the most absolute void. Crucially, its density remains constant, so as the universe expands, the total amount of dark energy grows, overpowering gravity and driving ever faster acceleration. The alternative model, called quintessence, proposes dark energy as a dynamic scalar field that varies over time and space. This is more intriguing because it could account for why the acceleration only became dominant in the last 5 to 6 billion years, potentially offering a richer evolutionary history for the cosmos. Ongoing missions like the Euclid Space Telescope are meticulously measuring expansion rates and growth of structures to distinguish whether dark energy is truly constant or a revolving entity. In summary, dark matter solves the mystery of missing mass that shapes cosmic structures via gravity, while dark energy addresses the enigma of the missing repulsive force that dictates the universe's ultimate fate through accelerated expansion. Together, they demonstrate that despite our many discoveries, from mapping the CMB to detecting gravitational waves from merging black holes, nearly 95% of the universe's true nature remains shrouded in darkness, challenging us to develop new physics, perhaps involving quantum gravity or extra dimensions. Finally, what about the question of what happened before the Big Bang? Unfortunately, this may be one query we can never answer within the framework of current physics. The no-hair theorem of cosmology, combined with the exponential inflation, implies that any information about the pre-Big Bang state was erased or rendered inaccessible. Modern physics can only describe events starting from about 10 to the power of minus 43 seconds after the Big Bang, just after the Planck epoch when quantum gravity effects dominated and our known laws began to apply reliably. This is the oldest, most intricate, and most enigmatic tale that contemporary physics allows us to explore and recount. It is an extraordinary odyssey from a dimensionless point to a cosmos teeming with countless galaxies, black holes, neutron stars, and perhaps even other forms of life. And yet, this journey of discovery is far from over, with upcoming telescopes like the James Webb Space Telescope revealing infant galaxies from the universe's dawn and particle accelerators probing fundamental forces. Humanity continues to push the boundaries of understanding, forever drawn to the stars that first sparked our wonder.